total power output or luminosity of the star. And by combining those, we can determine what the total surface area is of the star, and from that we get its diameter.
Now, that assumes that you can measure its luminosity fairly well and that you know something about its temperature from its color. Most of the time, they just simply appear as pinpoints of light, and it's impossible to actually resolve it. Although there are new instruments now called interferometers, which are capable of resolving even very tiny point sources, like stars. And in some cases, there have been direct measurements of stellar diameters.
VY Canis Majoris will not be a title holder forever. The red hypergiant is losing mass at the rate of almost 30 Earth masses or more per year.
The largest stars in the universe, like VY Canis Majoris, are actually dying stars. That as stars begin to die, they burn their nuclear fuel much less stably. They puff out over time.
VY Canis Majoris is probably only a few million years old. Stars that are as massive as it is don't live very long. They use their fuel up at prodigious rates. Then they swell up into this hypergiant state and only live there for a few 100,000 years, a very short time scale, and then rapidly explode.
VY Canis Majoris might have the largest diameter, but when it comes to possessing the most mass, there's another star that tips the scale. In the wide world of stars, there are many contenders vying for the title as the largest in the universe. But when it comes to stars, big can mean two different things.
When you talk about the biggest star, you could mean one of two things. You could either mean the star that has the largest diameter, or you might mean what its mass is. And mass is a measure of how much stuff you have. It's sort of like your weight when you step on a scale, how much matter your body is made of.
According to some astronomers, the most massive star is located in our Milky Way galaxy. It's part of a binary star system known as A1, which is actually two stars that orbit each other once every 4 days.
We find there that one of the stars appears to have a mass of about 115 times the mass of the Sun, and the other star is also enormous, about 84 times the mass of the Sun. So both stars in this binary are among the most massive stars that we have ever measured. There may be more massive stars than the combination in A1 in this star cluster, but that's the most massive that we've been able to measure directly.
These massive stars will live full but short lives.
Massive stars are hugely luminous. Sometimes they can outshine millions of stars in their neighborhood, but at a cost. Cost is they will run out of fuel faster than everybody else. And when they die spectacularly. They explode their guts and scatter it across the galaxy. So, the cost of living a high-mass life, a high-luminous life, the cost of living in the fast lane is that you explode at the end of your life.
A bright star may burn out faster and die sooner, but at the same time, those hot stars are cooking up elements that are essential for life. So without really massive stars, we wouldn't be here because you wouldn't get the iron in my blood and the calcium in my bones. All of those things are formed only in the most massive stars.
We humans need essential elements from massive stars. But we also need a planet with a firm surface to stand on. Planets come in two size groups: large gas giants like Jupiter and small rocky terrestrials such as Earth. In our own solar system, Jupiter is the largest planet, while Earth trails in 5th place. Yet even though Jupiter reigns supreme in our galactic zip code, it's not the biggest planet in the universe. The largest planet with a well-known radius is called TRES-4. It's named after the Transatlantic Exoplanet Survey that discovered it in the constellation Hercules in 2006.
TRES-4 is unusually large for its mass. We can actually directly measure its radius, and this particular planet has an unusually large radius. It's about 70% bigger than Jupiter, yet it has only about 80% of Jupiter's mass. That's about the same density as cork or even whipped cream.
If you look at Earth, it's a rocky planet, very dense. And then even the gas giant planets like Jupiter are compressed gas and water and other chemicals, very tightly compressed. This thing, TRES-4, is like a marshmallow.
Although TRES-4 is light for its size, it's about 18 times larger than Earth. Scientists aren't exactly sure how TRES-4 got so large. One theory is that the planet's extremely close distance to its parent star is cooking up a lot of chemicals in its atmosphere, which is trapping heat, much like greenhouse gases.
This particular planet is only about 5% of the Earth-Sun distance from its parent star, so it's very, very close. In fact, so close, it orbits its star every 3.5 days. So you can imagine how hot and how just blasted with sunlight this thing must be. Because the planet can't cool off, it can't shrink. Because when it's very hot, when gases are very hot, they expand. So this might be contributing to keeping the radius of this planet so very large.
TRES-4 may be a puffed-up planet, but when it comes to sustaining life, bigger planets don't offer prime real estate.
These giant planets really are just gas. There's no solid structure to them at all. There's nowhere to stand on them. So it's not a very likely place to find life, because life would have to continually be blown around in the atmosphere. And that's a hard thing to evolve from.
This planet would not be a very habitable place because it's so close to its parent star. It's getting blasted with radiation from its sun. So it would be a very hot and unpleasant place to be, at least for humans.
TRES-4 currently has the largest known radius. However, the planet could be bumped out of first place in the near future.
Scientists are finding new planets basically every day almost at this point. So it's quite possible that we will find another one that's even bigger than this particular planet anytime.
In addition to planets, scientists are also discovering new asteroids all the time. These are rocky bodies that didn't become planets. And the largest one may exist in our galactic neighborhood. In our own solar system, billions upon billions of leftover rocks that didn't become planets take refuge in the asteroid belt. Some are as small as grains of dust, and others are the size of nations. Ceres was the first asteroid ever discovered, and it remains the largest known asteroid to date. Named after the Roman goddess of plants and harvest, Ceres is about 600 miles in diameter, so it's almost as large as the state of California.
Ceres is so big that it contains 25% of all the mass in the asteroid belt. Ceres is so big that if you took all the other asteroids in the asteroid belt and glued them all together, they'd only be about 2 or 3 times bigger than Ceres.
Ceres' size sets it apart from the rest of the rocks in the asteroid belt. It would take the Apollo lunar rover 10 days to drive around the asteroid at 8 miles per hour. But in addition to its size, its other distinct feature is its round shape.
You have all these Idaho potatoes orbiting in the asteroid belt of the solar system, most of which are craggy chunks of rock. Ceres is large enough, massive enough, that its gravity has overcome the strength of the rocks that contain it. And anytime that happens, the shape becomes a sphere.
Because of its round shape, Ceres now holds a dual title.
The current definition of a dwarf planet is something that in fact is massive enough and has enough self-gravity to form itself into a round shape. And in fact, since Ceres is round, we also call it, in addition to being an asteroid, a dwarf planet. We know only a little bit about the composition of Ceres right now. We know that it's made primarily of rock, but it may also have water ice, and in fact, it could have clay inside it as well. The Dawn mission is actually going to go to Ceres and enter into orbit around it, and they'll bring a whole suite of instruments to bear on it. So we should learn a lot more about the composition of this unusually large asteroid in our own solar system.
Ceres may be the largest asteroid in our solar system, but it's a big universe out there.
It's quite possible that as we go on to exploring other solar systems outside of our own, that we may in fact someday find an asteroid larger than Ceres.
Our solar system contains some oversized objects. The largest planet, Jupiter, has the biggest moon, named Ganymede. Planet Mars actually contains the largest volcano, called Olympus Mons.
It's 17 miles tall, which makes it about 3 times taller than the biggest volcano we have on Earth. It's so tall that if you stood at the base of Olympus Mons, you wouldn't be able to see the top due to the curvature of Mars itself. So in our own solar system, the biggest things definitely have had a powerful shaping effect on the universe.
One might guess that the Sun would take top honors as the largest thing in our cosmic suburb. It's 1,000 times more massive than Jupiter. But is there something bigger?
The largest object associated with our solar system is the Oort cloud. And this is a very diffuse cloud of comets that literally extends about halfway out to the nearest star, Alpha Centauri. Alpha Centauri is about 4 light years away.
Astronomers estimate it would take the space shuttle hundreds of thousands of years to travel around the outer edge of the Oort cloud.
The Oort cloud is so dark and so distant that we really can't directly observe it. But what we do know is that comets come in from every direction on the sky. So there must be a spherical cloud of comets far away from us.
The origins of the Oort cloud remain puzzling. One theory is that it was formed early in our solar system. As comets fell in towards the forming sun, they were ejected into long orbits. Over time, their orbits threw them out into a giant cloud.
It's very far away, and it's filled with icy remnants that have just been left in basically the same state that they were from right around the time when our solar system formed, about 4.5 billion years ago. So they are, you could say, the archaeological remnants of the formation of our solar system.
The universe is comprised of things both big and small. But it's the large structures in space that challenge our understanding of how the universe works. Although astronomers have found many substantial objects, the quest to find even larger ones continues.
Astronomers are hoping to find new large planets, new huge superclusters, and learn more about the things that we've already seen. As technology improves with better telescopes, better detectors, newer surveys, we will be able to see farther into space and therefore hopefully discover even bigger things than we already know about.
החידה העתיקה בעולם מרתקת אותנו גם במאה ה-21.
About 3.5 billion years ago, life started.
איך הכל התחיל?
A couple of simple amino acids.
האם הגענו מגלקסיה רחוקה?
Life may not be the property of Earth itself.
או
Power and escape its bonds.
Holy cow! This is what an astronaut feels.
It creates and breaks the stars, the planets, the galaxies, and directs their cosmic roller coaster ride.
Gravity's our friend and our foe.
Without it, life as we know it would end.
The Earth would literally explode.
It is the magnificent and mystifying force that rules the universe. Gravity. Gravity is the most pervasive force in the universe. It is at work on massive and minute scales, on the routine and the extreme. A surfer needs it to hang 10.
When you ride a wave, you're going to slide down the front, and you're going to use that pull of gravity to get you going. It's your acceleration force. It's your accelerator. Gravity's your accelerator.
A skier uses it to race downhill. A snowboarder must have it to get big air. It acts on everything with mass, including us, 24/7, even when sleeping or standing.
Gravity here on Earth, of course, is always accelerating us down toward the center of the Earth, at 32 feet per second squared.
At a theme park, gravity is the galactic gas that makes roller coasters roar and people scream.
The gravity of the Earth pulls us down, and that's going to make us go really, really fast.
All objects with mass or energy, particles, people, planets, stars, and galaxies produce gravity. Omnipotent and omnipresent, gravity attracts, governs, warps, shapes, makes and takes all matter and mass in the universe.
So it's pervasive. It acts on all things through extremely large distances, and nothing escapes its pull.
It is gravity that holds our solar system together.
The force of gravity is basically that thing that holds us on the planet, keeps us from flying off.
It is the cosmic glue that binds all matter in the universe together.
If you were to imagine taking two dice and putting them perfectly at rest out in the middle of space and separating them by a centimeter, then what you'd see is that over the course of an hour or so, those two dice would slowly come together and touch.
Gravity made our world.
Our sun formed from a vast cloud of gas that gravitationally contracted. Similarly, our Earth formed through the gravitational attraction of little particles, little bitty things, gradually growing into a bigger and bigger object.
When it comes to gravity's pulling power, mass and distance matter.
It depends on the masses of each object, the amount of matter within each object. So it's proportional to the product of the two masses.
In other words, the bigger it is, the harder it pulls on other objects. But that's not all.
And it's inversely proportional to the square of the distance between them.
This means if you double the distance between two objects, the attraction or pull is only a quarter of its original strength. The pulling power of gravity lets it direct the motion and movement of all matter, however massive, in the universe.
So you have whole galaxies, for example, in orbit around each other. Clusters of galaxies all orbit around their common center of mass.
But it is the practical potential of harnessing this relentless force that has obsessed scientists for centuries. It would literally fall to Galileo Galilei, the 17th century truth seeker, to first recognize that gravity even existed.
Galileo found that objects having a different weight fall at the same rate. So here's a very heavy steel ball and a light ping pong ball of the same size. And if I drop them at the same time, they hit the ground at exactly the same time as well, because they fall at the same rate.
To illustrate Galileo's most profound gravitational discovery, that all objects, regardless of mass, fall at the same rate, we take a ride on the mega-fast Super Manly Escape at Six Flags Magic Mountain in Southern California. The theme park ride is the stage for a spectacular free fall demonstration. It will show what happens when a car full of people and a tennis ball fall from 415 feet in the air.
Okay, here we go.
All right.
The riders are shot up the 41-story tall tower at 100 miles an hour. With their eyes open, gravity will help them see a superhero.
Oh my God! Okay, I'm gonna drop this ball now, and oh my God, it's floating around. It's floating. It's floating. It's floating. Oh, the wind blew the ball away that time.
While we expect all objects to fall freely together, regardless of mass, on a windy day, results aren't always perfect.
All right. Oh my God.
At the very top of the ride, when upward motion has stopped, gravity takes over, and the downward free fall begins.
Oh God, I'm gonna drop this ball. It's gonna float. It's gonna float. Oh, it's floating. It's floating. Oh.
And then, for a few blissful seconds, theme park thrill seekers feel weightless, as if they are free of gravity, or in what scientists call zero G.
Oh, that one floated well. That one floated well. Oh man. I'm gonna try dropping the ball. Oh.
But zero G is just an illusion. In reality, gravity is running this ride. It's the force that yanks the car, the people, and the tennis ball, indifferent to their mass, back down to Earth at the same rate.
Oh, that's a fantastic ride. I mean, feeling oneself drop is amazing. But what's really great is dropping the ball and seeing it floating above my face. Now, I mean, it's falling. I know it's falling, but I'm falling at exactly the same rate. It doesn't matter how massive something is. It falls under the force of gravity at exactly the same rate.
Thanks to experiments like this, we now know that objects all fall at the same rate. But what would it take to launch a cannonball into orbit? When the famous British physicist Sir Isaac Newton saw the apple fall, that some say hit him on the head, it changed the world.
You got the apple falling from the tree, and he looks up and sees the moon in orbit around the Earth, and judges that not only is the apple falling to Earth, so too is the moon.
But could the moon really be falling? By thinking of a cannon and the trajectory of the ball it shoots, Newton used math to unlock a cosmic mystery. It came in his landmark publication, Principia Mathematica, in 1687.
Isaac Newton has a famous drawing, and in it he draws a planet and a little mountain. And there's a little projectile first kicked off the mountain, and it falls down a little bit. You give it more speed, it goes a little farther out.
Now say you could just increase the force all you wanted. It could go 50 miles, it could go 100 miles before it fell.
By adding more gunpowder, and with just the right angle of fire, a cannonball can be made to go faster and farther. Inevitably, however, gravity wins, pulling the cannonball back down to Earth.
The Earth is round and not flat, so Newton realized that if the cannonball is fired at sufficient speed, the cannonball would actually go into orbit.
For that to happen, Newton determined, the ball would need to be shot out of the cannon at 17,500 miles an hour.
It starts curving around the Earth, and he realized that there must be a speed where it goes completely around the Earth and hits you in the back of the head, never actually hitting Earth's surface. And if you duck, it'll just keep going, and lo and behold, you have an orbit.
But why doesn't the moon fall to Earth?
The moon also has some sideways motion. So for every little bit that it falls down, it also moves off in this direction, and the sum of all those motions is an orbit around the Earth.
Newton also realized that the Earth is in a giant free fall around the sun. With gravity forging the path, our planet rounds the sun like an endless cosmic roller coaster ride. Newton cracked the gravity code, and physicists are still using his ideas to solve all sorts of problems. Some of them stranger than others, like what would happen if a person tried to travel through a tunnel from one side of the planet to the other? In this wild scheme, you'd have to drive a straight-line tunnel right through the Earth and use gravity alone to propel a traveler down this so-called Gravity Express.
So suppose you've got one of these tunnels, and you jump in. Initially, the Earth is pulling down. You're going toward the center of the Earth, and so you're accelerating toward it. But as you pass through the center of the Earth and start going out toward the opposite side, the gravity of the Earth is trying to pull you back, so it's decelerating you.
So gravities actually have a braking effect. There's no fear of shooting out the hole on the other side of the Earth at some tremendous velocity and shooting yourself back into space. But in fact, you reach the surface of the Earth exactly, you will close to a perfect rest. In 42 minutes, you'll be there.
Whichever two cities you connect with a straight-line tunnel, it takes gravity exactly 42 minutes to get you there.
The journey from Los Angeles to Paris, 42 minutes. Suppose you wanted to go from Los Angeles to Tokyo, 42 minutes. It doesn't matter which path you take through the Earth, the journey is always 42 minutes long.
It takes Newton's math to figure out why this works.
If we connect Los Angeles to New York, taking a tunnel, obviously the tunnel will not go straight down, but it has to go down at an angle.
The angle slows the speed of descent.
But the distance is also less, and if you work out the equations, lo and behold, the two effects cancel, and you still get there in 42 minutes.
It takes 42 minutes regardless of the path you take. That's really cool.
Newton figured out what gravity does, but it took the brilliance of physicist Albert Einstein to work out why it was doing it. Einstein realized that gravity is really caused by huge objects like stars and planets literally bending space itself. Like a massive rubber sheet, space is curved when massive objects sit in it. In fact, Einstein proposed that the path planets take around their stars, their orbits, are all a direct result of this curvature of space.
He said that what an orbit is really something traveling in a straight line. When something is free-falling towards another object, it really is just traveling in a straight line through space-time. However, the curvature of space-time bends its path into a closed orbit, but space itself curves it back in on itself.
This revolutionary discovery came when Einstein, in the early 1910s, realized that orbits of stars and planets in the observable cosmos behave just as Newton's math predicted, except one, Mercury. Its orbit essentially wobbles.
Einstein described gravity as a curvature in space and time. And the orbit of Mercury works perfectly when you take that into account. Mercury isn't moving in flat space, but curved space around the sun. Then the orbit's perfect.
This curvature of space is at play in our own solar system.
Earth is simply following what it thinks is a straight line path, the shortest distance between 2 points, in this intrinsically curved space.
Einstein not only determined that mass warps space, it warps time, too.
So henceforth, Einstein proclaimed, physicists should not speak of space and time separately, but of space-time as one unified object.
While it's uncomfortable to many the first time you hear it, if you stop and think about it, it's actually quite obvious. If I'm going to make an appointment with somebody, I don't say, I'll meet you at 3 o'clock. That's not enough information. There's got to be a question that follows that. What is that question? Where? If I say